Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So imagine you have a $100,000 piece of heavy machinery, right?
Mm-hmm.
It's operating at absolute peak capacity on a factory floor, just humming along. And then suddenly, without any warning at all, the main drive assembly just shatters.
Oh, man. The worst nightmare.
Literally the worst. Metal fragments are flying everywhere. Production grinds to this catastrophic halt. And, everyone is just scrambling to figure out what went wrong.
Yeah, and the first thing everyone asks is, did the computer models fail?
Exactly. Was the math off by a decimal point? But no. In this scenario, the math was flawless.
Right.
The machinery tore itself apart simply because an engineer, well, they trusted a counterfeit stamp on a bolt. And the microscopic sulfur content in that fake steel caused a weld to crack from the inside out.
Yeah, and it's a scenario that plays out far more often than most people realize. I mean, we place so much faith in the digital perfection of computer-aided design, but the physical world is just incredibly unforgiving.
It really is, and that is exactly what this deep dive is all about today. We're kind of treating this session as a masterclass in electromechanical design.
A very necessary masterclass.
For sure, because our mission is to really bridge that massive, often treacherous gap between, textbook engineering theory and the messy, gritty, unpredictable realities of the manufacturing floor.
Because knowing the math is, well, it's really only half the job.
Exactly.
Yeah.
Knowing how materials actually behave when they're cut, bent, welded, and stressed, that's what separates a novice from a master designer.
Right. And to set the baseline for this entire discussion, we really have to address the core philosophy of a design engineer. If you look at the fundamental principles laid out in our source materials today, one rule just stands above the rest.
Okay, lay it on us.
Your absolute prime responsibility is to render a prototype functional.
Functional, not cheap.
Right. Safety and producibility are tied to that function, obviously. But costing and tooling, they absolutely must come second.
I can already hear, the product managers and the financial teams groaning.
Oh, they hate this.
Right, because they live and die by spreadsheets. Are we seriously saying we just ignore the cost of manufacturing when we're designing a product?
No, not ignore. But you absolutely cannot let cost dictate the initial functional requirements.
Gotcha.
Think about that broken machinery you just described. If a designer starts a project with the primary goal of cutting costs, they inevitably start making dangerous compromises.
Like swapping materials.
Exactly. They might swap out, say, a highly specific fatigue-resistant steel alloy for just a cheaper standard-grade steel.
Right, and on a spreadsheet, they're like, hey, I just saved 30 cents per unit.
Yeah, promotion time. But in the physical world, they just guaranteed that the component will shear under dynamic load after, maybe 6 months of use. And the cost of recalls, the downtime, the reputational damage, that will eclipse those initial savings by a factor of 10,000.
Yeah, you're not saving anything at that point.
You must design for flawless function first, and then optimize for cost only where the physics actually allow it.
I love that. Function dictates form, and physics dictates function.
Exactly.
So let's get into the physics. We're starting this masterclass with the raw materials themselves. Specifically, the invisible forces that are, constantly trying to tear our designs apart.
The fun stuff.
Yeah, there is a concept in the sources that feels almost like an oxymoron to me. Cold flow.
Ah, yes. Cold flow.
Like, how does a solid material just sitting there at room temperature actually flow?
It's weird, right? It really defies our everyday intuition about solids. We just assume that a block of dense plastic or like a piece of lead is perfectly static.
Right. A block is a block.
But cold flow, which is the gradual extrusion or physical deformation of a non-elastic material under a constant load, it happens continuously over time. The material is literally migrating away from the pressure.
Migrating. So it's not like dropping an anvil on a piece of hot glass where it squashes instantly.
No.
It's more like a creeping displacement. Like if I think about a heavy piece of furniture sitting on a carpet, and then months later you move the furniture and there are permanent dents.
Yes.
The material just slowly yielded,
Mm-hmm.
like squishing Play-Doh, but in super slow motion.
That is the exact mechanism just applied to critical machine components. Teflon, for instance, is notorious for cold flow.
Oh, really?
Yeah. Let's say you design a high-pressure fluid system,
Yeah.
right? And you use a thick Teflon seal, clamping it down hard with a set of heavy steel bolts.
Okay, makes sense.
On day one, the seal is perfect. The pressure holds. But over the next 6 months, the constant clamping force causes that solid Teflon to slowly ooze outward.
Just sneaking out the sides.
Exactly. And as it thins out, the bolts effectively lose their tension.
Oh, man. Which means your high-pressure system is suddenly going to spring a massive leak.
Yep.
And the maintenance team is going to come in and find the bolts completely loose, even though nobody touched them?
They'll think someone forgot to tighten them.
That's wild.
Yeah.
So how do you design around a material that refuses to just stay put?
Well, you have to build dynamic tension into the assembly. Instead of using standard flat washers under your bolt heads, you use something like a Belleville washer.
What's a Belleville washer?
It's a conical spring washer. So as the Teflon slowly cold flows and thins out, the Belleville washer continuously expands.
Oh, I see.
Yeah, it maintains a constant clamping force on the seal despite the material's migration. You really have to anticipate the movement.
You're treating the material as a living, shifting thing rather than just a static block on a blueprint.
That's a great way to put it.
Now, while Teflon oozes away from pressure, other materials bounce back, which brings us to a foundational concept, Hooke's law.
Right, Hooke's law is basically the bedrock of elastic mechanics.
It's the one we all learned early on.
Yeah. It states that a body acted upon by external forces will deform in direct proportion to the stress incurred, as long as you don't exceed the material's proportional limit.
Right, so if you apply 100 pounds of tensile force to a steel rod and it stretches 1 millimeter,
Then applying 200 pounds will stretch it 2
it's
millimeters.
perfectly linear, right up until you pull it so hard that it permanently deforms.
Exactly, meaning you've crossed the elastic limit.
But the sources highlight a nuance here that, well, it completely disrupts that clean, linear math that's called elastic hysteresis or damping.
Yeah, this is where the math gets messy. The digital model assumes that when you release that 200 pounds of force, the steel rod instantly and perfectly snaps back to its original zero state.
Just boom, back to normal.
Right, recovering 100% of the kinetic energy. But at the microscopic atomic level, materials are far messier. There is internal friction between the grain structures of the metal.
Internal friction. So as the atoms are forced to slide back into their resting positions, they're literally rubbing against each other.
Effectively, yes.
Yeah.
And as we know, friction generates heat. Because a tiny fraction of that stored mechanical energy is converted into internal thermal energy, the material does not instantly snap back.
Oh, wow.
There is a microscopic time lag and a slight loss of energy upon recovery. That loss is elastic hysteresis.
I see why this matters. If you have a component that is vibrating violently, like an engine mount or a suspension spring, that hysteresis is actually doing you a favor, isn't it?
It is.
It's acting as an internal shock absorber, converting the destructive vibrational energy into harmless heat over time, naturally damping the system.
You've hit the nail on the head. But the downside of continuous stress cycles brings us to the ultimate engineering nightmare.
Fatigue failure.
Exactly. High cycle fatigue failure.
I've always thought of failure in like two ways. There's static failure, which is like snapping a dry twig. You apply force, it breaks. And then there's, bending a paperclip back and forth until it gets hot and tears in half.
The paperclip is a really great example of low cycle fatigue. But in industrial machinery, we are dealing with high cycle fatigue.
Like what?
Like a rotating shaft or a connecting rod that might be pushed and pulled millions of times at loads well below its yield strength.
Millions of times.
Yeah. And the danger here, and a massive pain point for designers, is how highly ductile materials behave under fatigue.
Ductile materials being things like copper or soft iron, right? Things that you'd expect to stretch and give you a warning before they fail.
Exactly. If you pull a piece of copper in a static test, it will stretch dramatically, neck down in the middle, and finally tear. It gives you plenty of visual warning.
I would say, hey, I'm breaking here.
Right. But under high cycle fatigue, that same piece of ductile copper behaves completely differently. Microscopic cracks form at a surface, often starting at a tiny scratch or just a machining mark.
Okay.
And with every cycle, that crack propagates deeper into the material's grain boundaries.
And because it's just a hairline crack, you can't see the part stretching or deforming. It looks perfectly fine to the naked eye.
Until the remaining uncracked cross-section of the metal is so small that it can no longer support the load.
Boom.
At that instant, the ductile material suffers a sudden, catastrophic static failure that mimics a highly brittle material, like glass shattering.
Wow.
There is zero warning. This is why calculating the specific fatigue endurance limit, the stress level below which a material can theoretically endure an infinite number of cycles, is absolutely non-negotiable for moving parts.
That's terrifying.
I know.
Speaking of materials betraying us over time, the sources detail a phenomenon specifically affecting aluminum called stress rupture.
Oh, yes, aluminum. It's lightweight and incredibly versatile, but certain high-strength aluminum alloys have a very dangerous characteristic.
What does it do?
With stress rupture, the actual ultimate strength of the material degrades the longer it is subjected to a load.
That is wild. Wait, it's not moving, it's not vibrating, it's just holding a heavy static weight, and the metal is actively getting weaker as the calendar turns.
Yep. The atomic structure slowly slips along the grain boundaries under sustained stress. An aluminum beam might comfortably hold a massive static load for a year.
Okay.
But 3 years later, under the exact same load, the material's internal strength has decayed so much that it simply ruptures and collapses.
Just gives up.
Exactly. To prevent this, designers have to ensure the long-term static stresses remain safely below the fatigue endurance limit, carefully selecting hardened alloys that resist this atomic slip.
So with all these invisible traps, cold flow, hysteresis, fatigue, stress rupture, how do we actually qualify a material before we trust it in a machine? The sources mention the IZOD impact test.
The IZOD test is one of the oldest and most reliable ways to measure a material's toughness, specifically its ability to absorb energy during a rapid, violent collision.
We need to know how a material behaves when a sudden shock tries to tear it apart.
Exactly.
I was reading through the physical setup for this, and it's surprisingly brutal.
It is.
You take a 10-millimeter square block of the material, but you don't just hit a solid block. You machine a very precise V-shaped notch into one side of it.
That notch is critical. It acts as an artificial stress concentrator.
Like a weak point.
Right. It forces the fracture to initiate at a specific known point. We clamp the lower half of that notch specimen vertically in a heavy vise. Then a massive steel pendulum of a known weight is raised to a specific height.
You release the pendulum, it swings down and strikes the specimen right above the notch.
It shatters the metal and continues its swing upward. Now, if the material is highly brittle, it absorbs almost no energy when it breaks, so the pendulum swings very high on the other side.
Because nothing slowed it down.
Exactly. But if the material is incredibly tough, it absorbs a massive amount of the pendulum's kinetic energy to tear the atomic bonds apart.
Which means the pendulum's follow-through swing will be much lower.
Yes. And by measuring that final height, we calculate the exact foot-pounds of energy absorbed.
I love that. It's like the difference between striking a pre-scored piece of glass versus a solid block of thick acrylic. The glass just snaps and the hammer keeps moving.
Exactly.
But the acrylic fights the hammer, slowing it down as it bends and tears.
That is a perfect physical visualization of fracture energy.
All right, let's transition from sheer material impact to structural stability. I want to look at the mathematical side of long, slender machine parts.
The slender parts, right?
The sources give us the modified Euler's equation for ultimate load regarding unbraced machine members. These are columns or rods where the length is more than 6 times its width.
This is a classic failure mode known as column buckling.
Buckling, not crushing.
Right. When you push down on a short, thick block of steel, it will eventually crush. But if you push down on a long, slender rod of the same steel, it won't crush. It will bow outward and fold in half. Euler's equation mathematically predicts the exact force required to cause that buckling.
The text writes out the formula. It's P equals C times pi squared times I times E, all divided by L squared. Instead of just reading the letters, let's unpack the relationships here. P is the ultimate load that causes the failure.
Correct. The variables on the top of the fraction determine how strong the column is. C is an end condition constant.
What does this mean?
If both ends of the column are rigidly bolted to the floor and ceiling, C is a high number, meaning it's highly resistant to buckling.
Okay.
If both ends are just resting on rounded pivot pins, C is very low, because the ends are free to rotate as the collar bows.
Got it. Then we have I, which is the moment of inertia. I always think of this as the geometry of the cross-section. Like a hollow pipe resists bending much better than a solid rod of the same weight, just because the material is pushed further away from the center axis.
That's a great way to think of it. And E is the modulus of elasticity, which is just the inherent stiffness of the material itself versus aluminum, for instance.
Right.
But the most critical part of Euler's equation is the denominator, L squared, where L is the length of the unbraced column.
And this is where the math shows us why length is the ultimate enemy of a mechanical designer.
It really is.
Because the length is squared in the denominator, the width grows exponentially. Like, if I have a 2-foot rod and I decide to swap it for a 4-foot rod, I haven't made it half as strong.
No, you haven't.
Because 2 squared is 4 and 4 squared is 16. I've actually made it 4 times weaker against buckling.
And that exponential decay of structural integrity based on length catches novice designers constantly. It governs the design of every hydraulic cylinder pushing a heavy load, every long linkage arm in an engine, and every structural strut in an aircraft.
Which brings us to a massive misconception about how we handle these dangers, the factor of safety.
Ah, yes.
I know the basic formula, right?
Huh.
Working stress equals the yield strength divided by your safety factor.
Simple division.
Right. If a steel bracket breaks at 2,000 pounds, and I want a safety factor of 2, I design the system so it never sees more than 1,000 pounds. But the sources are highly critical of engineers just guessing these numbers.
Highly critical. For a very long time, slapping a factor of 4 or a factor of 10 on a blueprint was considered good engineering practice.
Just overbuild it.
Right.
You know,
It was actually known as the factor of ignorance. You didn't fully understand the dynamic load, so you just made the part 10 times thicker. But arbitrary safety factors are inherently dangerous in modern complex machinery.
Wait, how can making something way stronger than it needs to be end up being dangerous?
Because a machine is an interconnected system.
Okay.
If a sudden shock hits the machine, you want the cheapest, most accessible part to act as a mechanical fuse and break, absorbing the energy.
Oh.
If you arbitrarily overbuild that accessible bracket with a massive safety factor, it won't break. Instead, it will instantly transfer that destructive shockwave into the heart of the machine, destroying the $50,000 primary gearbox that takes 3 weeks to replace.
So you accidentally armored the bumper so heavily that the engine block cracked instead.
Exactly. This is why modern designers cannot rely on arbitrary guesses. They must utilize the strict allowable design stresses published by organizations like the American Society for Testing and Materials, the ASTM.
Or the American Iron and Steel Institute, the AISI.
Right. These codes are based on decades of destructive testing and empirical data. They provide exact allowable stresses for specific applications, ensuring the entire system yields predictably.
So the lesson is, let the organizations that have broken millions of pieces of metal do the math for you.
Exactly. Trust the data.
That logic is the perfect bridge to part 2 of our syllabus, shaping the parts. We understand the raw materials and the math. Now we have to actually manipulate them on the factory floor. Let's start with sheet metal.
Oh, sheet metal. It seems deceptively simple in CAD software. You draw a thin rectangle, click the bend tool, and fold it up.
Easy, right?
But the physical shop floor is fraught with manufacturing constraints that CAD ignores completely.
The sources highlight a classic rookie trap here, designing a tiny flange. They use the example of a designer specifying a 0.375-inch, so a 3/8 of an inch bent lip on a relatively thick piece of steel.
Right. The designer sees a perfect right angle on their screen. But on the floor, sheet metal is bent using a massive machine called a press brake.
How does that work?
The metal rests on a bottom die, which has a V-shaped groove cut into it. A heavy top die, shaped like a wedge, presses the metal down into the groove to form the crease.
And here's the physical limitation, right? That V groove in the bottom die has to be a certain width to accommodate the thickness of the metal.
Precisely. If the V groove is an inch wide, and your designer asks for a flange that is only 3/8 of an inch long, well, that piece of metal is physically too short to bridge the gap across the V groove.
Oh, man. So what happens?
When the top die comes down, the metal doesn't bend. It just slips and falls straight down into the hole.
It just plops in?
Yeah. To make that tiny bend, the shop has to use highly specialized, expensive bottoming dies, which drastically increases the tooling cost and setup time.
That's just a limitation of physical leverage. Another massive issue with sheet metal is raw material inconsistency. The text discusses mill tolerances, specifically with hot-rolled steel.
This is a harsh reality check for tight tolerance designers. Hot-rolled steel is manufactured by squeezing glowing hot slabs of steel through massive rollers at the mill.
It sounds chaotic.
It is. And as the metal cools, it shrinks and scales unevenly. This means that a single sheet of 11-gauge hot-rolled steel is not perfectly uniform in thickness. It varies from the center to the edges.
But the designer doesn't know that. They draw a complex bracket folded from 11-gauge steel, and they slap a tolerance of plus or minus 1/64 of an inch on the final dimension.
And the press brake operator laughs at them.
Right.
Because the raw material itself varies by more than 1/64 of an inch before it even goes into the machine.
The metal is already out of tolerance before you touch it.
Exactly. If the metal happens to be slightly thicker in one spot, the press brake bends it slightly differently and the final dimension changes. You cannot demand microscopic precision from a macroscopically lumpy raw material.
So what's the fix?
If you need that precision, you must pay significantly more for gauge-accurate, cold-rolled steel or design the assembly to absorb those physical variations.
The material dictates the tolerance, not the designer's wishful thinking. Now, what about round stock? There's a trap mentioned here regarding standard cold-drawn steel rod.
Oh yeah, the shaft trap.
Let's say I'm building a conveyor belt and I need a 2-inch steel axle for the rollers. Can I just buy a 20-foot stick of standard 2-inch cold-drawn rod, cut it, and slide standard bearings onto it?
If you try that, you are in for a nightmare on the assembly line.
Why?
Standard cold-drawn steel rod has a relatively loose tolerance spread on its outside diameter. The rod might be exactly 2 inches in one spot, 1.995 inches a foot later, and 2.005 inches at the end.
And bearings are precision components.
Extremely precise. If the rod is slightly undersized, the inner race of the bearing will sit loose. When the machine spins up, that loose fit will chatter, vibrate, and destroy the bearing in hours.
Ouch.
And if the rod happens to be slightly oversized, the assembly workers will try to hammer the bearing onto the shaft, completely crushing the delicate ball bearings inside before the machine is even turned on.
Just brutalizing it. So the solution being?
You must specify shafting grades of steel. These are raw materials that have been turned, ground, and polished at the factory to incredibly strict outside diameter tolerances. They are specifically calculated to mate perfectly with the interference fit of standard bearing inner diameters.
Okay, let's move from bending and cutting metal to forming it from scratch. Castings are well known, pouring molten metal into sand. But the sources rave about a different process for high-volume, complex parts. Powder metallurgy, or PM.
Powder metallurgy is practically magic for small, intricate components like gears, cams, and levers.
Instead of melting the metal, you start with highly engineered metal powders.
Right. You pour this powder into a precision machine die, and massive hydraulic punches compress the powder with tons of force until it becomes a solid, fragile shape called a green part.
Then you bake it.
Yes, you pass it through a sintering furnace. The heat is just below the melting point, but it's high enough to cause the metal particles to fuse together at an atomic level.
The text mentions this is a secret weapon because it eliminates secondary machining operations. I can picture trying to make a gear out of a solid block of steel. You have to turn the outside on a lathe, use a specialized gear hobbing machine to cut every individual tooth.
Drill the center hole.
Yeah, and if you want a hexagonal hole to fit on a hex shaft, you have to use a broach to violently scrape out the corners.
It takes 5 different machines, 5 operators, and a lot of wasted metal chips. With powder metallurgy, you engineer the shape of the die once. Every time the press cycles, out pops a perfectly formed gear with the teeth and the hexagonal center hole already finished, ready for the furnace.
But the text also lists strict design rules for powder metallurgy, because the physics of compressing powder are very limiting.
Very limiting. The most critical rule is understanding the axis of compression. The top and bottom punches can only move strictly up and down. Therefore, you cannot design any reverse angles, undercuts, or horizontal holes on the exterior of the part.
I picture like packing wet sand into a bucket at the beach. If the bucket is wider at the opening and tapers down, the sandcastle slides right out.
Exactly.
But if you try to pack sand into an hourglass, shaped wide at the top and bottom but narrow in the middle, you can pack the sand in, but the rigid bucket can never be pulled off without completely destroying the shape.
That is exactly the physical limitation. The powder metal part must be able to eject vertically from the rigid die walls. The sources also mention keeping wall sections thick. Remember, before the part is baked in the furnace, it is only held together by the mechanical interlocking of the powder grains.
So thin walls will just break.
Thin walls will simply crumble as the part is ejected from the press.
And there's a really interesting warning here about finishing PM parts. Avoid specifying electroplated finishes. Why is dunking a sintered gear in a protective plating bath a bad idea?
Because of the inherent nature of the process. Even after sintering, powder metal parts retain microscopic porosity.
Tiny holes.
Yeah, there are tiny invisible voids throughout the material. If you submerge that part in a highly caustic electroplating bath, the acidic chemicals seep deep into those microscopic pores like a sponge.
Oh, gross. And you can't just rinse that out, can you?
You can't. The surface is plated and looks beautiful, but weeks later, the trapped caustic chemicals begin to bleed out. They literally rot the part from the inside out, causing massive subsurface corrosion.
Wow.
You have to use specialized sealing processes before plating, which drives up the cost, or simply specify an oil-impregnated finish instead.
Corroding from the inside out is terrifying, which is a perfect segue into part 3. Holding it together. We've got our raw material, we've shaped it, now we have to assemble the machine. We're looking at fasteners, interferences, and tolerances. I want to start with a major real-world issue the sources highlight, something that sounds like industrial espionage. The counterfeit bolt crisis.
It is a massive, ongoing threat to global manufacturing and infrastructure. We are seeing a flood of counterfeit fasteners imported into the supply chain.
It's bolts.
Fake bolts. These are bolts stamped with the official head markings, indicating they are high-strength structural grades, but they are manufactured from vastly inferior, uncontrolled scrap steel.
The sources share a chilling specific example. A company ordered what were supposed to be AISI 304 stainless steel bolts.
Right. 304 is a highly common, reliable austenitic stainless steel. But during a routine welding process on the assembly line, these bolts literally cracked completely open.
Just from welding.
The heat of the welding arc caused massive, instantaneous structural failure.
So they sent the broken pieces to a metallurgical lab. What did the lab find?
Well, the chemical analysis revealed it wasn't 304 stainless steel. In fact, it didn't conform to any known standard American stainless series. The counterfeiters had used cheap, random alloys. Most devastatingly, the analysis showed the fake metal contained 10 times the maximum allowable limit of sulfur.
10 times. What exactly does a massive dose of sulfur do to steel when you hit it with a welding torch?
Sulfur is sometimes added to steel to make it easier to cut on a lathe, but it is absolute poison for welding. Under the intense heat of the welding arc, the excess sulfur segregates and forms iron sulfide along the grain boundaries of the metal.
And that's bad because
Iron sulfide has a much lower melting point than the steel itself, so as the weld pool cools and contracts, the grain boundaries literally tear themselves apart. It's called hot cracking.
So the counterfeiters saved a few dollars on raw material, and in doing so, created a fastener that self-destructs the exact moment you try to integrate it into a welded assembly.
Exactly. And the takeaway for designers is that in critical applications like aerospace, pressure vessels, heavy lifting equipment, you cannot simply trust the physical stamp on the bolt head.
It's just too risky.
Hardware must be certified with documented chemical mill test reports and often independently lab tested to verify the metallurgy is actually what it claims to be.
Let's step down from catastrophic failure to sheer mind-numbing frustration.
Okay.
The sources call out wrench clearances. Every shade tree mechanic has cursed out an automotive engineer because a bolt was placed half an inch away from a solid engine block, making it physically impossible to get a tool on it.
Oh, I've been there. It is a classic disconnect between the digital world and the physical world. In CAD software, a designer can easily click and drag a bolt into the deepest, tightest corner of a machine.
The computer screen doesn't care. The 3D model looks perfectly clean.
But the designer completely forgets that a human hand, holding a thick-walled steel socket wrench, has to physically envelop the head of that bolt to turn it.
Right. You have to account for the radial clearance of the tool itself. If you don't leave room for the socket to spin or for a box wrench to swing its arc, the assembly line workers will either not be able to build a machine or
they will improperly torque the fastener using makeshift tools, guaranteeing a loose joint and future failure.
So sometimes we use bolts, but other times we use brute force. Let's talk about interference fits, also known as force fits.
Oh, these are fascinating.
This is where you machine a steel shaft slightly larger than the hole you want to put it in, and then you just smash them together.
It's an incredibly effective, permanent fastening method that relies purely on immense friction, with no extra hardware needed. You might machine a shaft to be just a few 10,000ths of an inch larger than the inner bore of a heavy steel gear.
How do you get them together if it's bigger?
To assemble them, you often use thermal expansion. You plunge the shaft into liquid nitrogen to shrink it, and you bake the gear in an oven to expand the hole. You slide the frozen shaft into the hot hole, and as they return to room temperature, the metal expands and contracts back to its original dimensions, locking together with terrifying force.
But what happens to the math when you cram a larger piece of metal into a smaller one?
Massive internal stresses are generated, and the mathematical pitfall here is that designers often try to calculate those stresses using simple, flat surface friction equations.
You can't do that.
You cannot do that. The sources emphasize that you must treat the fitted parts mathematically as thick-walled cylinders expanding and contracting against one another.
Because the pressure isn't just pushing straight down, it's pushing outward radially in a complete circle.
Exactly. We call it hoop stress. The oversized shaft is frantically trying to push the inner diameter of the gear outward.
And if you get the math wrong?
If the designer miscalculates the interference tolerance by even 1/1000th of an inch, the hoop stress will exceed the ultimate tensile strength of the gear material. And the gear will literally split completely in half the moment the temperatures equalize.
Which brings us directly to the nightmare of dimensioning and tolerancing. Specifically what the sources call the cost trap. There is a deeply ingrained assumption that specifying tighter tolerances on a blueprint automatically results in a higher quality, better machine.
It is the fastest way to hemorrhage money on a manufacturing run. Tolerances dictate the manufacturing process, and processes dictate cost. Let's say you have a simple steel pin that just acts as a door hinge.
Okay.
A tolerance of plus or minus 10/1000ths of an inch is perfectly fine. The machinist can turn that out rapidly on a standard CNC lathe in seconds.
But if a nervous designer decides to tighten that tolerance to plus or minus 1/1000th of an inch, just to be safe,
Suddenly, the lathe isn't accurate enough. The machinist has to cut the pin slightly oversized on the lathe, move the part to a highly specialized cylindrical grinding machine, and slowly grind away microscopic layers of steel to hit that tight number.
so you just turned a $1 part into a $20 part.
Multiplied by 10,000 units. For a door hinge that doesn't function any better, tolerances must be strictly balanced against functional necessity.
The sources also point out a specific physical reality that designers constantly forget, leading to ruined assemblies. The plating trap.
This error happens daily in machine shops. A designer painstakingly calculates a beautiful, precise slip fit between a steel axle and a bronze bushing. The tolerances are tight. The math is verified.
Perfect on paper.
But right before releasing the drawing, they add a quick note. Zinc plate all over for corrosion resistance.
They forget that chemistry takes up physical space.
Exactly. Electroplating or hard coat anodizing on aluminum actually deposits physical layers of material onto every surface of the part. If the electroplating process adds 0.002 of an inch of zinc, it adds it all the way around the circumference of the axle.
So the diameter of the axle just grew by 0.004 of an inch.
And suddenly, the perfectly calculated slip fit becomes a massive interference fit. The axle will absolutely not fit into the bushing. The assembly line halts. Thousands of parts have to be scrapped or laboriously stripped and remachined, all because the digital model didn't account for the physical thickness of the chemistry.
It all connects. You change the chemistry, you change the geometry. Let's keep moving. Part 4. Making it move. We've bolted the static frame together. Now we're looking at the kinetic components. Springs, linkages, and electromechanical systems. The sources take a deep dive into springs, and frankly, they make springs sound like highly stressed, ticking time bombs.
Springs are fascinating because they are designed to operate continuously at the absolute ragged edge of their material's structural limits. They are constantly cycling near their yield point. And the foundational rule of spring design is respecting the spring index.
The index is a mathematical ratio. It's the mean diameter of the coil itself divided by the diameter of the wire used to make it. So if I have a coil that is 1 inch across, wrapped from wire that is a 1/4 inch thick, 1 divided by 0.25 is 4. My spring index is 4.
Right.
Why is this ratio the holy grail for spring manufacturers?
Because it dictates both the manufacturability and the internal stress of the metal. Think about how a spring is made. Heavy steel wire is forcefully wrapped around a solid steel cylinder called a mandrel by a coiling machine.
Yeah.
If your spring index is very low, say under 4, it means you are trying to wrap incredibly thick wire tightly around a very small mandrel.
Which requires immense brute force and massively distorts the molecular structure of the steel on the inside of the curve.
You are introducing extreme permanent internal stresses into the wire before the spring has even seen its first operational load. It is highly prone to fatigue failure.
Okay, what about the other end of the spectrum? If you specify an index over 10, you have very thin wire wrapped into a very large coil.
It's floppy, like a slinky.
Yes, slinkies are cool, but not great for heavy machinery.
Right. High-index springs are physically unstable. They don't hold their shape well. They become a tangled nightmare in the shipping boxes, and they buckle sideways under compression. The engineering sweet spot for a reliable, manufacturable spring is an index between 4 and 10.
Even if you get the geometry right, the sources highlight a massive, invisible chemical threat to springs, specifically when you try to protect them from rust. They call hydrogen embrittlement the silent killer.
This is one of the most insidious failure modes in mechanical engineering. Let's say you take your perfectly designed high-strength steel spring and you drop it into an electroplating bath to coat it with zinc.
Just trying to be a good designer and stop rust.
Right. But the electrochemical plating process involves acids and electrical currents, which liberates atomic hydrogen in the solution.
And these hydrogen atoms are incredibly small.
So small that they literally diffuse right into the crystalline lattice structure of the high-tensile steel wire. They sneak in between the iron atoms and congregate at the grain boundaries.
Acting like microscopic wedges being driven into the metal.
Precisely. The trapped hydrogen drastically reduces the ductility of the steel, making it incredibly brittle. If that plated spring is not treated immediately, it is doomed.
The sources outline the strict cure for this. You have to bake the hydrogen out.
Immediately after plating, typically within 1 to 3 hours, the springs must be placed in a high-temperature oven and baked for several hours. This thermal energy excites the hydrogen atoms, allowing them to diffuse back out of the steel matrix, restoring the spring's ductility.
If a supplier decides to save some money on the electric bill and skips the baking process, what happens?
Catastrophe. The internal stress caused by the trapped hydrogen is so severe that hydrogen embrittled springs have been known to violently shatter into multiple pieces, just sitting quietly in their cardboard shipping boxes on a warehouse shelf.
Oh my God.
Zero external load applied. The internal pressure alone tears the steel apart.
That is the ultimate example of invisible physical forces destroying a digital design. And sometimes the material itself is just wrong. The text details a material mix-up where a company rejected an order of 5,000 large compression springs.
The rejection occurred because the springs were taking a permanent set. A machine would compress them, and they just wouldn't spring back to their original length.
They completely violated Hooke's law by yielding immediately.
The original blueprint correctly specified ASTM A228 music wire, which is an exceptionally high-tensile, premium, cold-drawn spring steel designed for severe, continuous stress. But because the springs failed so spectacularly, the engineers sent samples to a metallurgical lab.
How does the lab prove what went wrong?
They cut a cross-section of the wire, polish it to a mirror finish, etch it with acid, and place it under a high-powered microscope. They are looking at the martensitic microstructure via a photomicrograph.
Cool.
By analyzing the visual crystal pattern of the grain structure, the lab proved definitively that the manufacturer had loaded their coiling machines with ASTM A229 oil-tempered steel.
Which is a significantly weaker, cheaper grade of wire. But to the naked eye on the factory floor, a spool of A228 and a spool of A229 look practically identical.
Visually identical, but metallurgically worlds apart. The A229 wire simply lacked the tensile strength to handle the calculated load it yielded on the very first cycle and ruined 5,000 components.
The sources also detail a physical manufacturing defect. A torsion spring, the kind with straight legs extending from the coil, like you see on a clipboard or a mousetrap, failed after only 1,000 cycles. And it wasn't the wrong metal, and it wasn't hydrogen.
It was a microscopic tool mark. To form the straight legs of a torsion spring, the coiling machine bends the wire sharply around a steel block or mandrel. In this specific case, the manufacturer's bending mandrel had an edge that was worn and far too sharp.
Oh, I see where this is going.
As it bent the wire, it pressed a tiny microscopic indent, a nick, into the surface of the steel.
And because the spring is cycling under heavy load, that tiny nick becomes the focal point for all the stress.
It acts as an aggressive stress riser. The bending forces concentrate entirely on that microscopic scratch, initiating a fatigue crack. With every cycle of the spring, the crack propagates deeper until the leg snaps clean off.
So easily avoidable, too.
Extremely. A designer can prevent this by explicitly specifying generous, controlled bend radii on the engineering drawing, forcing the manufacturer to use properly rounded tooling.
All right, let's look at moving parts that don't bend, but pivot. Linkages. Specifically, the classic 4-bar linkage. We see these everywhere: windshield wipers, heavy clamping mechanisms, oil pump jacks. The sources make a surprising admission about them. The math is incredibly hostile.
You have 4 solid bars connected by 4 pivoting joints. Trying to solve the complete kinematics, meaning mathematically calculating the exact position, velocity, and acceleration of every single point on those bars throughout a continuous 360-degree rotation, generates equations that become monstrously complex very quickly.
If the math is that brutal, how do engineers actually optimize these high-speed linkage mechanisms? Do they just guess and check?
They rely on physical testing augmented by technology. Instead of getting bogged down in pages of advanced calculus, modern engineers build functional physical prototypes. They hook them up to motors and run them at operating speed.
But human eyes can't see what's happening at thousands of RPMs.
Exactly. So they use high-speed photography, shooting at 1,000 to 12,000 frames per second.
So they film the prototype running at full speed and then sit down and watch the playback in extreme slow motion.
Exactly. By analyzing the high-speed footage frame by frame, engineers can visually observe the physical realities that the math might miss. They can see exactly where the linkage binds, where the metal physically flexes under dynamic load, and where cam followers bounce off their tracks.
It allows for rapid, intuitive design corrections based on physical reality rather than pure theory. We can't talk about movement without touching on gears. The sources provide a specific formula for the velocity of a spur gear. I know we aren't supposed to get bogged down in reciting formulas, but let's talk about why the velocity of the gear tooth matters.
Okay.
The formula takes the pitch diameter, multiplies it by RPM, and uses a constant to give us the velocity in feet per minute. So V equals 0.261, 8 times the pitch diameter, D times the RPM.
What that formula is doing is translating the rotational speed of the gear, the RPM, into the actual linear surface speed of the gear teeth slicing through the air and engaging with each other.
Why does an engineer care about the linear feet per minute speed of a gear tooth?
Lubrication and wear. If 2 massive steel gear teeth are meshing at high surface speeds, the friction is immense.
Right.
If the velocity is too high, the gear teeth will literally wipe the lubricating oil film right off the metal surface, resulting in bare metal-on-metal contact, extreme heat, and rapid catastrophic wear. Knowing the exact surface velocity allows the engineer to specify the correct viscosity of oil or design forced lubrication jets to keep those teeth protected.
Before we wrap up this section on moving parts, the sources take a fascinating, almost combative stance on engineering terminology. The author clearly has a strong opinion on the word mechatronics.
Oh, the author's highly adamant about this. Mechatronics has become a very trendy buzzword in the last couple of decades, used to describe modern systems that combine mechanical engineering, electrical circuits, and computer control.
Like a robotic arm or a modern car engine. But the author rejects the word.
Completely. The source argues that mechatronics is an inaccurate, fabricated term. The proper, historically established term is electromechanical design.
Interesting.
The author points out that electrical components have always been utilized in electronic and mechanical systems. Even a modern microchip, the heart of the computer aspect, is fundamentally an electromechanical system component at its physical base. The author urges the industry to respect the established 100-year-old nomenclature rather than inventing flashy new jargon for marketing purposes.
A little interdisciplinary beef to keep things spicy.
Always.
Let's cool things down and talk about finishes. Part 5. Finishes and the endless war against corrosion. The sources hit us with a jaw-dropping statistic right out of the gate. The $125 billion problem.
That is the estimated annual cost of corrosion damage in the United States alone. $125 billion eaten away by rust and chemical degradation.
That is an insane amount of money.
It is a relentless physical force that operates 24 hours a day, regardless of whether the machine is running or turned off.
And a huge contributor to this astronomical cost is galvanic corrosion, which you described earlier as the battery effect. How does a mechanical assembly accidentally turn into a battery?
It comes down to the galvanic electromotive series. Every metal in existence has a specific inherent electrical potential. When you place 2 dissimilar metals in direct physical contact and you introduce an electrolyte, which in the real world is simply moisture from rain or humidity, you create a galvanic cell.
You have literally built a destructive short-circuited battery.
Yes.
Walk us through the specific example from the text using the extremes of this scale.
Let's look at magnesium. It sits way down at the active end of the scale with an electrical potential of negative 2.37 volts. On the other end, you have gold sitting at the noble end with positive 1.50 volts. But let's use a more common industrial example, steel and copper.
Okay, steel is relatively active and copper is relatively noble.
Correct. Let's say you bolt a heavy steel bracket directly onto a copper grounding plate, and it sits outside in the rain. The chemical reaction initiates immediately. Because of the difference in their electrical potentials, negatively charged electrons physically flow out of the steel bracket through the bolted connection into the copper plate and dissipate into the moisture.
The steel is literally bleeding electrons into the copper.
Yeah.
What is the physical result of that flow?
Rapid, localized corrosion. The steel acts as the anode, literally sacrificing its own atoms to fuel the electrical reaction. It rapidly converts into iron oxide rust and physically rots away.
But the copper is fine.
The copper plate remains perfectly pristine, protected by the sacrificial destruction of the steel. This is why mechanical designers must intimately understand the galvanic scale. If you must join dissimilar metals, you have to design electrical isolation between them, like rubber gaskets or specialized coatings to stop the electron flow.
Speaking of coatings, we touched on the plating trap, where coatings ruin dimensional tolerances. But the sources mentioned that plating also has strict geometrical design rules. Specifically, the danger of blind holes.
A blind hole is a hole drilled into a block of metal that does not go all the way through to the other side. It's essentially a cup. When you send a part out for electroplating or anodizing, that part is submerged into a series of massive vats containing highly caustic cleaning acids and liquid plating chemicals.
And that blind hole fills up with the liquid.
Exactly. When the crane hoists the part out of the vat to move to the next step, the flat surfaces drain off. But the liquid trapped in the bottom of that blind hole has nowhere to go. It sits there.
Yikes.
Even after the plating process is supposedly finished, those trapped, highly concentrated caustic chemicals will slowly eat away at the bare metal at the bottom of the hole, ruining the structural integrity of the part.
How does the designer prevent that? Do we just outlaw blind holes?
You can't always outlaw them, but you must design for drainage. The sources give a specific fix for hollow weldments, like large square tubes or box frames that need to be plated. A designer must explicitly mandate the drilling of 0.250-inch weep holes at the lowest corners of the assembly.
Weep holes, just to let it drain.
Right. These small holes serve no structural purpose. They exist purely to allow the plating fluids and acids to drain completely out of the interior cavities when the part is lifted from the vats.
You're designing the part not just for its final function, but for its journey through the chemical baths. Moving on to part 6. Electrical engineering basics for the mechanical designer. The sources argue that bridging this gap is no longer optional.
It is absolutely mandatory. A century ago, a mechanical engineer could design purely steam or belt-driven mechanisms. Today, almost every mechanism is actuated, driven, or controlled by electricity. A mechanical designer who refuses to understand basic electrical properties is effectively designing in the dark.
The text highlights the IACS standard for measuring electrical conductivity. What does IACS stand for, and why is it important?
It stands for the International Annealed Copper Standard. The engineering community needed a baseline to compare how well different metals conduct electricity. They chose pure ETP copper electrolytic tough pitch copper and set its conductivity value at exactly 100%. Every other metal is measured against that standard.
Copper is the gold standard, ironically.
Exactly.
But we don't always use copper. Aluminum wiring is used constantly in aerospace and automotive applications to save weight.
And that is where the mechanical designer must understand the trade-off. A highly common aluminum alloy used for conductors is 6101T63. On the IACS scale, that aluminum alloy has a conductivity rating of around 61%.
It's only about 3/5 as efficient at moving electrons as copper.
Which means if you are swapping a heavy copper cable for a lighter aluminum one, you cannot use the same diameter wire. Because the aluminum resists the current flow more, you must specify a significantly thicker aluminum cable to carry the exact same electrical load without overheating and causing a fire.
Speaking of wire thickness, the sources bring up a measurement system that confuses a lot of people outside the electrical industry. Circular mills, we all know, standard house wiring, 12-gauge, 14-gauge. But when you get into massive industrial cables, they stop using gauges. Why?
The American wire gauge system is a geometric progression, but it breaks down and becomes cumbersome for massive power cables. In heavy industry, we need to know the exact cross-sectional area of the copper to calculate its current carrying capacity. But calculating the area of a circle involves pi, which makes the math messy when you are bundling hundreds of small wires into one massive cable.
So they invented a new unit of measurement to bypass the pi math.
Exactly. They created the circular mill. A mill is 1/1000th of an inch. A circular mill is simply defined as the area of a perfect circle that has a diameter of exactly 1 mill. By defining the unit this way, you completely eliminate pi from the calculation of the wire's area.
So if I have a massive solid copper rod that is 3/4 of an inch in diameter, 0.75 inches, which is 750 mils, I don't need to do any complex geometry.
You don't. You just take the diameter in mils 750 and square it. 750 times 750 is 562,500. So that rod has a cross-sectional area of roughly 563,000 circular mils. In the industry nomenclature, the Roman numeral M stands for 1,000, so we call it a 563 mccentimeter cable. It is a brilliant, streamlined standard that allows mechanical and electrical engineers to communicate precisely about massive power requirements.
And all that copper power usually flows into a motor to spin a mechanical shaft. The sources define two highly critical types of motor torque that a mechanical designer must design around: locked rotor torque and breakdown torque.
When a machine is turned off, resting on the factory floor, there is massive static friction in the bearings, the gears, and the heavy physical load it carries. Locked rotor torque, also known as starting torque, is the absolute maximum twisting force the electric motor can produce at the exact millisecond it is energized, while the shaft is still physically locked at 0 RPM.
If the motor's locked rotor torque isn't higher than the static friction of your machine, the motor just hums, overheats, and melts its insulation. It can't break the physical stasis.
Exactly. Now, once the machine is up and running at full speed, you worry about breakdown torque. This is the absolute maximum torque the motor can generate while running before the magnetic fields essentially slip, the speed abruptly drops, and the motor forcefully stalls out.
So if a massive rock falls into the rock crusher you designed, creating a huge spike in resistance, the motor hits breakdown torque and violently stops. The mechanical designer has to ensure the shafts and gears can handle that sudden, violent stall without snapping an F.
Exactly. The electrical limits dictate the mechanical shock loads.
We have covered an immense amount of ground, diving deep into the physics, the chemistry, and the floor-level reality of electromechanical design. We have reached Part 7, the Q&A segment. As mandated by the masterclass structure, I am going to fire off the most common, painful questions and misconceptions engineers are constantly fighting, based entirely on the source material we just dissected. Expert, are you ready to rapid-fire some solutions?
I am ready. Let's solve some floor problems.
Question 1, a classic management complaint. My engineering team is building a prototype, and it's incredibly expensive. How do I avoid disastrous prototype failures while keeping costs down?
The harsh reality. You cannot build a valid prototype based on cost cutting. The entire purpose of a prototype is to physically validate the complex math and material science of the engineering drawing. If the drawing calls for an expensive, heat-treated 4340 alloy steel, and management forces the shop to substitute a cheap, mild steel just to save money on a test unit, the physical tests are entirely invalid. You are testing a compromised design. When the cheap prototype fails, you learn nothing about the actual design, and you've wasted all the time and money. Build it exactly to print, and test it strictly to established ASTM or ANSI standards.
The prototype is a physical truth teller. Don't lie to it. Question 2. A designer is pulling their hair out. I calculated the dynamic load perfectly. My math is flawless. Why do my highly stressed steel springs keep shattering on the assembly line?
If the math is flawless, the manufacturing physics failed you. Look for 3 specific culprits we discussed. Number 1, did you electroplate the spring for rust protection but fail to mandate a strict post-bake? If so, atomic hydrogen embrittlement is shattering the crystalline structure of the steel. Number 2, examine the broken legs of the spring under magnification. Is your specified bend radius too tight, forcing the coiler to use a sharp mandrel that created microscopic stress riser nicks? Number 3, trust but verify your supply chain. Did the manufacturer accidentally load the machines with cheaper oil-tempered wire instead of the high-tensile music wire you specified? Send a broken sample to a metallurgical lab and demand a photomicrograph of the grain structure.
Question 3. A machinist's nightmare. I designed a sheet metal enclosure. I specified standard tight tolerances on my drawing, but the machine shop is aggressively rejecting the prints, saying it's impossible. Why?
Because your digital drawing ignores the physical reality of the raw material and the chemistry. If you are using hot-rolled sheet metal, the thickness of the raw steel right out of the mill varies more than the tight tolerance you are demanding from the press brake operator. You cannot force microscopic precision onto lumpy steel. Alternatively, you fell face first into the plating trap. You perfectly toleranced a tight-fitting slot and tab on the enclosure, but you forgot that the thick layer of hardcoat anodizing or zinc plating you requested physically adds thickness to every surface. Your perfect digital fit became an impossible physical interference.
The chemistry took up the empty space. Final question. A welding disaster. I specified stainless steel hardware for my welded frame to prevent rust. Why did the welded joints immediately crack down the center?
You chose the wrong chemistry for the heat. You likely specified a high-carbon stainless steel, which becomes incredibly brittle when subjected to the intense thermal shock of a welding arc. Or, far worse, you purchased uncertified hardware and got hit with counterfeit bolts loaded with sulfur, which caused catastrophic hot cracking at the grain boundaries as the weld pool cooled. For welded assemblies, you must strictly specify low-carbon austenitic stainless steels, like AISI 304L or 316L. The L literally stands for low carbon, specifically engineered to survive the heat of the torch.
That brings us to the end of the syllabus. We've traced the journey of a machine from the microscopic atomic boundaries of raw steel through the brute force of the press brakes into the caustic chemical plating vats and finally to the electrical currents that bring it to life.
It is a gauntlet of physical realities.
And as we close out this deep dive, I want to leave you with a provocative thought that builds on everything we've discussed today. We are entering an era where AI and generative design algorithms can instantly optimize complex 3D models for weight and theoretical strength. The computer can do the Euler buckling math in milliseconds. But AI lacks physical intuition. An algorithm doesn't know what a dull drill bit sounds like when it chatters against cheap, hot-rolled steel. It doesn't instinctively feel the oily residue of trapped plating acid bleeding from a powdered metal gear. It doesn't understand the sheer physical frustration of trying to swing a wrench in a 1-inch gap on a dirty assembly line. The math on the screen is rapidly becoming commoditized. But the human engineer, the person who deeply understands the gritty, chemical, and physical realities of the manufacturing floor, that person is the ultimate, irreplaceable bridge between digital perfection and physical reality. The floor always wins. The master designer simply learns how to negotiate with it. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.